This is ECSx, a new approach to game development in Elixir. First off, I want to thank every one of you for coming out. I really appreciate it. Thanks to Jim and the staff here at ElixirConf for doing all this. And thanks to Dockyard for sponsoring me to be here today. I am Andrew Berrien. I'm a senior engineer at Dockyard. My GitHub and email address are on screen if you want to reach out if you have any questions afterwards. I live in Austin, Texas, and fun fact, I'm a blue belt in jiu-jitsu. If you don't know about jiu-jitsu, look into it. It's a blast. All right, so first I'd like to talk about a few goals of the ECSx project. First off, I'd like to make everyone in this room a game developer. I think most of you in here have at least one idea in your head floating around for a game, and hopefully ECSx can help bring that game idea to life. The second goal is to make back-end game development fast and simple. Game development is a lot of work, and hopefully ECSx will make the process smooth and easy for you. And lastly, we want to get good performance in game development with Elixir. Elixir has a lot of great things going for it in game development and otherwise, concurrency, scalability, fault tolerance. But there's also concerns people have around game development in Elixir, particularly regarding data immutability and message passing. So first, I'd like to take a look at some of those concerns and discuss them. Immutability and message passing can become a performance concern in game development. So, for example, let's say we have a game with ships. The ships could be spaceships, they could be ships on the high seas, however you want to think about them. But let's say those ships have several attributes. They have hit points, attack damage, attack speed, armor, etc. Now let's say that your ship is in combat and gets attacked by another ship and takes 10 damage. So we're going to have a worker process to handle this. So the first thing that we need to do is copy the ship into the worker process. This is because processes in Elixir are isolated, and so one process isn't going to be able to read the memory of another process. So we copy the ship data from the data layer process into the memory heap of the worker process. Next, let's say that we have 2 armor on the ship, so let's say armor is a direct reduction in damage. So if you're getting attacked for 10 damage, let's say that's going to reduce it by 2, and so you're really taking 8 damage. So in order for this to happen, we're going to create another copy of the ship. Due to data immutability, when we need to change something about an object like this ship, we're going to create a new copy of the ship with that particular attribute changed. So here we have another ship with 42 HP after taking 8 damage. Then, lastly, we need to copy this new ship back into the data layer to replace the existing one. So as you can see, in order for this ship to take damage in combat, we've created 3 copies of the ship. Now maybe that wouldn't be too big of a deal, but in this case, you'll notice we have 7 different attributes: attack damage, speed, position, velocity, and these are not changing at all over the course of this operation. But yet we have to keep copying them around and creating more data for this operation. Now this is where the performance concern comes into play. And there's various ways to architect your application in order to solve this problem. One of those ways is ECS, or Entity Component System. Now, with ECS, the data for your ship is stored separately. Each one of those attributes is going to be stored separately in what we call a component. So we have a HP component, attack damage component, attack speed, etc. In the data layer, there is no ship. Instead, each one of these components is going to have a unique ID that they will all share. That's where the E in ECS, the entity, comes into play. An entity in ECS is more of a metaphysical object that you could construct in your mind because all of these components have the same ID in the back. So let's say we have the same operation. You have a ship that's under attack for 10 damage. In ECS, we're only going to query the components that matter for that operation. The only ones that mattered were the hit points and the armor. So in this case, we query those and copy them into the worker process. Then 10 damage minus 2 armor means 42 hit points. So we're going to create another copy of the HP component with a value of 42, and then send it back to the data layer. So in this case, we've still made 3 copies, but we've copied significantly less data. Next, how does the worker process in this scenario know what to do? When you are taking 10 damage, how did that worker process know to query the hit points, reduce the armor, etc.? This is where systems come into play. Systems hold all of the logic for your game's backend and organize it according to feature. So each one of these systems is going to run n times per second, where n is the server's tick rate. If you're not familiar with game development and tick rate, the tick rate is the smallest unit of time for your game. So this can be between 20 and 60 usually. And so let's say we have a server tick rate of 20. So each tick is going to be 1/20th of a second. So you're going to write system logic in a way that it will process 1/20th of a second worth of game logic, and then run that 20 times per second. Generally, how a system works is first it's going to fetch a list of relevant components, and then it's going to update the components. So that's super vague, but we'll see an example of system logic soon. First, let's take a look at what the developer experience looks like when using the ECSx framework for your game. ECSx mostly is going to handle all of this with generators. So game development could, especially with ECS, could require a lot of boilerplate to make all of this happen. So instead, we want you to write absolutely 0 boilerplate. Instead, you're going to run generators for just about everything. So first thing after creating a new application and bringing in the ECSx dependency is you're going to run the mix ECSx setup generator. This is going to inject some configuration into your app's config files. And it's also going to set up a manager module. The manager module is a gen server which will handle some things such as the data initialization upon your app startup, but it will also keep a list of all of the components and systems in your application. Speaking of components and systems, these will also be handled with generators. So for each component type in your application, meaning we saw 8 examples of them earlier, hit points, attack damage, attack speed, armor, etc. Like these are component types. So for each component type that you'll need to model your application's data, you're going to run the ECSx gen component generator. And you'll provide 2 arguments to this. One is the name of the module, and then the other is the Elixir type of the value that that component is going to hold. So that could be integer, string, atom, etc. Next, you'll run ECSx gen system for each one of the features in your game. So it could be that you have a kind of one-to-one relationship where each component type has a system which operates and keeps that component type updated. But we also saw an example earlier of a system that might be seen as like a composite system where it's actually relying on 2 different component types, the HP and the armor, and that system is going to use both of them in order to fulfill its logic. So this is going to take 1 argument, simply the module name of the system. Then lastly, we have another generator for tags. Tags is a feature in ECSx which is not present in all ECS implementations, but I do find it useful enough to include in ECSx. A tag is a subtype of components, and it's mostly going to be used in cases where you would like to have, say, a Boolean type of component. So for example, let's say you want to have a component type called isHuman to show that an entity is human. Now, in order to have an isHuman type, like a Boolean component like this, you would have to create one of these components for every single entity in your application, whether it's human or not. So if you're creating a tree, a rock, and a ship, like all of these are going to get isHuman false, whereas humans will get isHuman true. I think that a much better way to do this is to simply only give the isHuman component type to entities that are actually human, and then not give it to those that aren't. So tags, in essence, are a component that doesn't need to store a value because the mere presence or absence of that tag is all the information that you need to know. If it has the tag, it's human. If not, it's not human. All right. So once we've run these generators, we're actually almost finished. We just have one more step left to go until our game's ready to play, and that is to write out the system logic. So when we ran our system generator, it's going to create a system module with a run function. And by default, the run function doesn't have any logic in it. It's just going to return OK. So what we need to do is we need to write out the logic, which is going to run each game tick for that particular feature. So let's take a look at an example. And I'm going to go line by line through this code. So first off, let's say that we have an under attack component type, signifying that a ship is under attack. Now, attacks could work a number of different ways. It could be just a one-off thing where you get attacked, you take damage, and that's it. But for the sake of the example, let's say that an attack in this case is more like a laser beam or a flamethrower, something that is consistently dealing damage to the ship until the attack ceases. So we're going to call the function getAll, which comes generated when you generate the under attack module. You're going to get an API to work with that under attack component. So one of those is getAll, which is just going to get all of the under attack components. And how a component is going to look when you query it is a tuple with two elements. The first is a reference to the entity. Now remember, entity is not an actual ship. It's just a unique ID that references the ship in those components. The second element is the amount of damage that the ship's going to take per game tick. And with these two pieces of information, we can run our system. So the first thing that we need to do with that is to use that entity reference in order to call the getOne function in our HP module. That will get us our current HP for the ship. We're going to call the same getOne function for the armor rating. And then once we have the current HP and the armor, now we can call update. And we'll update the hit points of that entity. And so in this case, we're using a kind of simplified formula. You might be able to see the problem here, which is that if the armor rating is greater than the damage being taken, then the ship is actually going to gain HP. So ideally, this formula would have some kind of min validation to make sure that you can't take less than 0 damage. But for simplicity and font size sake, we're going to just use current HP plus armor minus damage. And the result is going to be saved into that new HP component. And with that, that's everything we need for our backend to be running. So let's take a look at another feature of ECSx, which is persistence. So you've created these components for all of the entities in your game, but if you need to shut down your server for any reason, when you start it back up, all of the component data will be gone. And maybe this is okay if you have a very short-lived game, but if you're running an RPG where players are questing and gaining experience and growing, they'll probably not be very happy if the server restarts for an update and then they start back at level 0 again. So persistence is something that comes built in out of the box with ECSx. And how it works is when you go to add a new component, like let's say we're spawning a character, and that character needs to have some hit points. Now, if this is a character that's just a little monster that you fight over and over again in order to farm gold or experience, maybe it's okay for it to not be persisted and have to be reloaded back from scratch when you start the app again. But maybe, like I said, maybe this is a real character that a player has put a bunch of time into and wants to make sure that something like their hit points is persisted across app restarts. So all you need to do is add this option as a third argument, persist true. If you don't pass persist true, then the default is false. And so components that have the persist true options set are going to be periodically backed up. And when you shut down your app and start it back up again, it's going to read from the most recent backup and load that component data. The backup frequency is configurable to whatever you want, so it could be every tick, or it could be every hour, or anything in between. The default implementation for this is it's going to dump all of the component data into a file system. However, we know that this might not be robust enough for many applications, so we also have an implementation of persistence that you can bring in optionally as a separate library called ECSx Persistence Ecto. And as you may have guessed, if you're using Ecto, this will save the component data into an Ecto database to be loaded later. Thanks to Mike Binns for his work on this feature. Next, a question probably many of you are wondering now is, well, you've talked a lot about the back end. What's the deal with the front end? Now, ECSx is designed to be front-end agnostic. You can use any front end you want. We generally have been advising using live view in our tutorials just because it's the simplest and lowest barrier to entry. However, if you have a favorite JavaScript front end or something else that you want to use, you should be able to use ECSx with this successfully. One caveat is that front-end clients are only going to have read-only access to the components. This is because you don't want the front-end client to be updating a component at the same time as one of your systems is updating the same component in the back end. This could cause data corruption in a number of ways. So instead, what you're going to do is have your front-end client call this function client events add. And this is going to create a new client event, and the two arguments that you're going to pass here are the reference to the entity, that ID, that references what this client event is about. And then the event argument can be literally anything you want. So this could be an atom that says player spawned, or maybe it needs to be something more complex. Maybe it's a tuple with the atom player moved, and then also some metadata about like what direction it moved in. This can be anything because you're going to pattern match on it in the back end. So in the back end, in one of your systems where you have write access to components, you'll call the get and clear function. And this will give you a list of all of the client events that have fired off in the last game tick. And then it will also clear them to ensure that when you call this function the next time, you don't get any duplicates. You don't want to handle the same event twice. And then you write any logic that goes along with this in your system, just like we showed before. All right, so now we're at the part of the talk where I'd like to show you a sample application, a quick demo. And so first, let's take a look at what an application using ECSx actually looks like. So this is taken from the tutorial project, which can be found in the documentation. And so we've created a Phoenix app and ran a bunch of generators and added system logic and a front end. So the first thing is a folder of components. So we have all of these generated components here, some of them we already saw in the previous example, but there's also some additional ones regarding cooldowns and projectiles, etc. Each one of these is simply a module that's going to exist for the purpose of the API, and you just have this use ECSx component macro in there, which is going to inject all of those functions like we saw earlier, get one, get all, etc. Then this players folder, this is just phx gen auth, Phoenix's built-in authentication system for players to log in. And then let's take a look at the systems. So we have an attacking system first off, and we see the run function. And the first thing that's going to happen is we're going to get all of the attack target components. And then for each one of those attack targets, we're going to check cooldowns and attack range and see if we're ready to launch that attack. And if so, we have logic to fire that attack off. Next is the client event handler system. So here we're going to call that get and clear function that we talked about earlier to get a list of client events. And for each one, we'll process one. And so we've got just a couple events here. One is spawn a ship. So we're going to create all of the components that are necessary in order to spawn a new ship. Then we also have move and stop move events with directions where we'll simply update the velocity that that ship is moving at. Then a cooldown expiration system. We get all of the attack cooldowns and remove them when they expire. A destruction system to check all of the ship's hit points to see if any are equal or less than 0, and if so, then we destroy it by removing select component types from it. The driver is going to check X and Y velocities and then update the X and Y positions accordingly. We have a projectile system to get all of the projectiles, here using tags. And for each projectile, we're going to most likely continue to seek that projectile towards the target. Otherwise, maybe we'll destroy the projectile if the target's already been destroyed. And then lastly, we're going to find all of the ships that are currently seeking a target. And if an entity does not have a target yet, then we're going to look for a new target for it. So that's the systems. Then we have some Phoenix-generated stuff here, and then the manager. So the manager is, like I said, simply a gen server. It's going to initialize some data. So when you start up your app, it's going to generate 40 NPC ships in your game for you to make combat with. Then it has a list of all of the component types and a list of all of the systems. And these functions are automatically updated when you run the generators, so you actually shouldn't have to touch the component or systems functions. The one exception is if you want to change the order in which systems run, you can come in here and change that there. So that is the backend. So now let's take a look into ship web, the front end. So all of this here is just stuff that comes by default with Phoenix, except for the game live. And this is our front end that we've created for the game. So first, we have some authentication going on here for the player to log in and then spawn their ship. We have some logic to keep the front end updated by reading components. Then we have events for key down and key up. And for each one of those keyboard input events, we're going to create a client event with that client events.add. And then here we have our render function. So let's take a look at this. With our implementation that we're using in the tutorial, we create a simple SVG. And first we have the background. The background is just blue ocean. Then on top of that, if the game is loading, we're going to have loading text. If the game's not loading and it's ready to go, then we're going to display your player ship. We're going to display the projectiles. We're going to display the other ships. And then we also have some hit points, or in this case, hull points, text in the corner to let you know how much longer you have before your ship is destroyed. And that's that's everything we need. So let's take a look at what this is going to look like. So we'll hop over into the game, and here we go. So here we have our ocean, we have a ship, and we can move the ship around. And as we get the ship close to other ships, you'll see we can fire cannonballs at them. This is automatic with the targeting system. Once you fire enough at the same ship, it's going to be destroyed and removed. If you get within another ship's attack range, you'll notice that ship will fire back at us. And you'll see our hull points in the top left being reduced. Now, another feature in ECSx that's going to not come in the standard library, but an optional dependency is the LiveDashboard. So as you probably know, Phoenix comes with the Phoenix LiveDashboard, which allows you to inspect various metrics and statistics about your running Phoenix application. So if you're running a Phoenix app and using Phoenix LiveDashboard, you can install an optional dependency, the ECSx LiveDashboard. And so this is going to create an extra page in there, ECSx, and when we click on that, this is going to show us the total system load. And so the point of this is that we talked earlier about the tick rate and said that a tick, for example, might be 1/20th of a second. And you need to run every system in your application every tick. So there's a limited amount of time before your systems will start taking longer than the tick, in which case the ticks will start backing up, and eventually your app will start lagging and maybe crash from having too many messages in the queue. So this is to provide you a simple interface to be able to see how much of that tick is currently being used by your systems. So in this case, you can see that our systems are only taking 4% or now 3% of the time that it has. And so we're pretty safe. If we were to see something like 90%, then that would be very bad, because if a few more players join and the load increases, then we're in the danger zone. So if that is the case, we also have the run times of each individual system. So this would allow us to see which system is really giving us the most problems and be a target for optimization. So in this case, the targeting system we can see is taking most of the time. So if we were in a case where the total load was in a more problematic area, then we would probably want to first start looking into the targeting system. And so we could optimize this by looking for a more efficient algorithm. We could introduce concurrency very easily since we're in Elixir. We could also reach for things such as NIFs, or even introduce NX if this is a computationally heavy system. Another feature of the dashboard is to see the components. So we're going to see how many of each components exist, but also be able to see what the value is. So we can see for each one of those entities what the armor rating value is and whether it's being persisted in the database. All right, so there's our demo. So let's hop back over here. Skip over these slides about LiveDashboard because we already showed that. And lastly, I want to talk about what's next for ECSx. First and foremost, optimizations. ECSx is designed to be fast. If it's not fast, then it's not going to work. So already, we've gone through several different iterations of the implementations of various functions to optimize them. We've done heavy benchmarking to make sure that the functions that you're calling out of the box are as efficient and fast as possible. However, there are some optimizations that we've found where they're more use case specific, like they might be helpful for your particular game or one system or one component type, but not others. So we are looking into some optimizations that might be toggleable, and depending on your game and your use cases, you might turn them on or turn them off. So we have several of those ideas coming down the line. Another thing is I get a common comment that I receive about ECSx is that so far it's been particularly geared towards real-time games and simulations. And that by nature, ECS is more geared towards real-time games. However, I'm constantly asked about support for turn-based games, and even hybrid games where some of the game is real-time and some is turn-based. Like you can imagine some JRPGs where you have a real-time world map, but then you enter into a turn-based combat of sorts. So currently ECSx does support this, but it's not necessarily the focus, and you can feel that. You can feel that you might have to do some workarounds in order to make the game as you'd like it to be. So in the future, we'd like to make turn-based games really a first-class experience in ECSx and provide better support for that. Another is the tutorial project. The tutorial project is generally people's first introduction to ECSx when you get into the project. Like it can sometimes feel overwhelming to start if you haven't listened to this talk. So the tutorial project is the recommended place for people to start, where it will explore all sorts of common features that you would want for your game and how to write out those systems and organize your application. We want to continue expanding upon this tutorial project to not only explore more features, but also more front ends as well. Currently, we just have this live view front end in SVG, but as a front end agnostic framework, we do want to have examples of all sorts of front ends, particularly live view native. This is a big goal of mine, is to find a way to implement ECSx games in live view native so that your game is not tied to just one particular target, but you can create your game and then also deploy it on mobile and native applications and web all at the same time, and more. And that's the end of my presentation. Thank you all for coming out. I have a GitHub, and Hex ECSx is also on Hex. Want to also give special thanks to my friend and mentor Mike Binns for all of his contributions to the project. I couldn't have done it without you.